Hello everyone. So in this today, I will discuss mainly about the evolution of water model. So for this session, this is only up to 20th century. Okay, so that's almost up to 3 decades, 30 years. So I try to make it as brief as possible. So this is not any kind of like very scientific, like very hard discussion. So it's a kind of history. Okay, so I think I can start. So if any one of you add any points, or if any one of you know anything about that, so you can share with us. Okay, so I think we can start. Okay, so basically that, as you all know, that this water model. Okay, so this water model context, or this thing, like if I start from a pre-computer era, so this thing starts in the year of 1932. Okay, so I'll just write it briefly. So 1932. So obviously there's a pre-computer era. So in 1932, like people like Armeke and physics first spectroscopically prove the V shape of water molecule. Okay, and after that, at 1933, Barnell and Fowler first proposed the realistic interaction potential for water. So these two are like major scientific breakthrough in the context of water model in the pre-computer era. So in 1932 and 1933. Okay, so the first 1932 is something else, like, right? It's the proofs of the
This is done with isolated water or vapor water or liquid water? I think liquid vapor water.
Yes.
Okay, because liquid water is complicated to spectroscopically.
And this is a major breakthrough, like 1932 and 33. So these two scientists, one is Barnell and another is Fowler. So these two scientists first proposed the interaction potential for water. So for this paper, I can write the, if anyone wants to read. So this one. So this is about the pre-computer era. Now come to the main thing. So which is the after computers come into the picture. The first thing in 1953, three scientists, Metropolis, Rosenbluth, and Taylor, so first present the Monte Carlo sampling scheme for water. Okay, so in 1953, three scientists. Okay, so it's Metropolis, and Taylor. So they first present the Monte Carlo sampling scheme. And now after that, in 1957, okay, so again two scientists like Alder and Wainwright. So they first performed the molecular dynamic simulation of water. Okay, so this is the first molecular dynamic simulation of water in the year of 1957. So you can note out first MD simulation. After that, in the year of 1969 and in the year of 1971, okay, so these two year is very important in the context of like first computer simulation. Okay, so to like in 1969, Barker and Watts, and in 1971, Rahman and Stellinger first published the paper in the context of computer simulation of liquid water. Okay, so that's why these two paper is a landmark paper. If any one of you want the paper, so I can share. So, and after these two work, so these two work I can write as a first computer simulations of liquid water. Okay, so after that, in the year of 1976, okay, so in this year, like Clementi and his group derive a pair potential for water from ab initio calculations.
Subhajit,
So
1957 MD simulation of water, or before that you write first computer simulation?
no, so this year, like this Anisur Rahman and Stillinger and Berkan and Watts, so this is the first published computer simulation of liquid water. Okay, and in 1957, so this is the first performed molecular dynamic simulations.
Okay, not on water means.
Not on water.
Okay.
In 1976, so this is for water, and this is the first pair potential derived, the Clementi derived a pair potential from ab initio calculations. Okay, so pair potential they have derived from ab initio calculations, and then like raised like 1981, 1983. Okay, so then these people did try to determine the accurate and simple pair potential for liquid water, and at the end of 1993, so then the first ab initio calculation of liquid water comes. So this is the first ab initio calculation. Okay, of liquid water. Okay, so that comes. Okay, so then if you see the timeline, so the mainly starting from 1932, so although there's a pre-computer era, and the computer era comes around 1950, so to 1933 the journey goes on. So today basically we'll discover like how people encounter such few problems and how people solve it in terms of water models. Okay, so this is the brief I want to say, okay, in this portion. So as you know, like the water model, like in the previous few discussions we talked a lot about like water models, like force fields basically, like ab initio and the polarizable force field, reactive force field, these things. So as you all know that uh, like major no force field is like kind of exactly accurate, we can say. So that's why I want to say this discussion, okay, so this topic. So in this water model section, like the first water model, like the interaction potential, you can say basically, is published by Barnell and Floor, which is called a VF water model in 1933, as you see. So this one, so this is called a BF water model, Barnell and Floor water model. And after that, like if we see, like majority of the water models are empirical. Okay, so in these empirical water models and some quantum calculations, people try to model water to, like, people keep in mind some aspects like the how the hydrogen bonds and form, how people can designate how hydrogen bond in their water model. So these things come one by one. So I want to introduce few water models. So like some of these talks, some of you don't know about water model. So I want to introduce few about that. Like majority of the models, so what I will discuss, the majority of the models are empirical, and these are the based on the calculation that show that the hydrogen bond in water dimer like, can be understood as the, you can say, as the competition between the attractive interaction potential energy and the repulsive internal electronic kinetic energy of water molecule. Like for this attractive interaction potential energy, so that thing uh, we can approximate from the classical electrostatic interaction. But these internal electronic kinetic energy, so that things come very later, like how people can designate this thing, that I will come. And this is the hydrogen bond context, and after that this charge distribution. Okay, so charge distribution, how people like how what in a water model, like the charge distribution is generally modeled by point charges on the nuclei, as you all know, like SPC. So in SPC, what happens? This charge distribution of is generally modeled by point charges on the nuclei. Okay, so not only that, people tried with adding one or several, like, additional fictive sites located in the plane of the molecular flame and sometimes out of it. Okay, so like in SPC we know, like it's you can write that it's modeled by point charges on the nuclei. Okay, and like as I said, like after that, like people tried with additional fictive sites. Okay, so like this BF model, as I said, and you can, all of you know, the T4P. So in these models, like add fictive sites in the plane of the molecular frame. Okay, so in this model, there is additional fictive sites located in the plane of the molecular frame. Molecular frame, and people tried with not in the plane of the molecular frame. They add lone pairs, like some famous model like BNS model, ST2 model. So in these models, they add fictive sites which are out of the plane, okay, out of the molecular plane. Okay, so in this, like BNS model and ST2 model, so they, like, something they have tried with the exact tetrahedral geometry. Like suppose this one is oxygen, this one is hydrogen, and they have located charge lone pair at this position, this minus q -q5, right? So these are the plus q. Okay, so these angles Okay, so these angles are basically like exact tetrahedral angle. We will try it with that. Okay, and after that, if we see to prepare a water potential or water model, uh, people tried the electronic repulsion between molecules is mostly encountered by a linear zone potential centered on oxygen. So in this linear zone potential, so it incorporates the dispersion energy also. So in that concept, like this interaction or like the attraction and dispersion context, in that context, like some water model comes like where this repulsion and the dispersion terms are treated separately. Okay, like the one water model I can say like tips. So in this water model, they have tried this to separate this repulsion term and dispersion term separately. And not only that, there is one model like NSPCE. So in this model, they have tried the exponential function in this linear Jones repulsive term. Okay, so if you can want to see the flavor, like people tried many things. Okay, so to reproduce some water property, so that I will come later, like, and then in this after this linear Jones terms, okay, so then few force field like SPC, AF, and central force model, so they introduce the flexibility of the molecule. Okay, so by allowing the intermolecular vibrations and these things. So after that thing, like few force fields, so in that come to SPCF and central force field model, central force model. Okay, and after that, like few water model like SPCP, CKL, and R pole. So these are the models, so where people uh, try to include the many body effects. Okay, so in that context, so the what models that they have developed by a set of point charts. Okay, so whose magnitudes they choose as a to produce the dipole moment of the gas phase, and they assign a point polarizability to the oxygen atom. So that we can see in the recent what few water models also. And not only that, like after that, as you know, like few for water model like SPCFQ, okay, T4PFQ. So these are the fluctuating charge. Okay, so which take into account the intermolecular charge transfer, so which is induced by the local field. Okay, and after that, like finally, people made few ab initio based force field at that time. I'm talking like few ab initio based force field like MCY, MCHO, NEMO. Okay, so these are few ab initio based force field people tried to made at that time. Okay, so in everything, like people uh like what people tried, like as you know that gas phase dipole moment, which is around 1.9 dB. So but in the liquid phase, the dipole moment of water is higher. So at that point of time, very early that point of time, people try to enhance the dipole moment with their water model. Okay, so for this liquid state. Okay, so how far they can able to do it, so that I will discuss. Okay, so the first thing, like after making the water model, the first thing you have to do, you have to test it. Okay, so the first few like you can say like 1960s to 1980s, people tried their water model with and tested the reproducibility or tested the ability of their water model at ambient condition like 298 Kelvin watt, but ambient condition properties of water. But after these 80s, so people uh, become concerned about the uh, water properties which is the away from the ambient conditions. Okay, so in general, by testing, as you all know that people calculate the density of the liquid, heat of vaporization, self diffusion coefficient, and RDS, and temperature of maximum density, some critical parameters, dielectric constants, and these things. And of course, the second virial coefficient, surface tensions, heat capacity, that things also. So in the first, if you made a water model, so the first thing you have to test, which is the liquid density. Okay, so as you know, like at 298 Kelvin, the experimental water density is something 0.997 gram per cc. Okay, so there is one review paper. So those, okay. So if you see this plot, so they made a very good plot. So the first is rigid force for rigid water model, and this one is for the flexible water model, and the last one is for polarizable water model. Okay, so if you see, they have marked this experimental water density by this dotted line. If you see, the some water model is very good at that point of time, so they uh, reached the target value, which is 0.997. Like if I mark these T4P, SPCE, T5P, DEC model, and some models which predicts too small value, like the CF model, MCI model, NEMO model. So this predicts too low value. Okay, and some model predicts too large value, like this BF model. So this predicts too large value. Okay, so but these liquid water density context, so we can say like like most of the water model agrees well with this experimental value. But this density of liquid is very sensitive. Okay, so because uh, for this ab initio calculation, like the small inaccuracy in the determination of exchange correlation energy, so that gives you a very erroneous value. Okay, because uh, this absence of the long range correlation. Okay, so that gives a erroneous value in the liquid density, but still it's adjustable, that like most of the water models gives at least reasonable value in terms of liquid density. Okay, so then the next thing comes, which is the heat of vaporization. So the heat of vaporization context, if you see, so this dotted line shows the heat of vaporization of experimental gas, and this solid line basically says the heat of vaporization for like the average, like the classical water, you can say, for the classical water, which is 11 kilocal per mole they have designated. So if you see in that context also, few water model uh, gives good value. Okay, so few water model are significant, so like SPC, if so these water model, you can say, so this gives reasonably good result with that. But this kind of for this heat of vaporization case. Okay, so heat of vaporization is very much important concept. So as you know, like uh, this quantifies the importance of hydrogen bonding in water. Okay, so
Subhajit, what is the solid line means? Dotted line is experiment.
the solid line they have designated as this line as a for the value of classical water. Okay,
Classical means
so
model water or what?
model water, yes, the
Okay.
classical mean like theoretical model water they have designated.
Means
Okay, so
model
which
means which model they use? Means water model for a water model simulation result. This is solid line or
this
some
is the
analytical data.
complete theoretical simulation result they have used. Okay, so some hypothetical classical water, so they have uh, what can I say, like some hypothetical classical water they have assumed, and they have calculated these they have estimated this heat of vaporization of that classical water, which comes around 11 kilocal per mole, and these values set as a benchmark to validate like all the simulation results. Okay.
Any particular model is used, or this is, I think, analytical might be some.
uh, that I need to check, like analytical, I have to check like what exact thing they have used at that point.
Okay, just we'll discuss. Can see later.
Mhm.
Mm.
Okay. Okay. So after that, if we compare the next thing, which is the uh, diffusivity. So as you know that this self-diffusion coefficient is very much important because it's measured the mobility of water molecule. Uh, it's an indicator of the influence of hydrogen bond on the translational motions between the water molecules. So as an experimental value for water, as you know, like they have marked this experimental value with this dotted line. The experimental value is something around 2.3 into 10 to the minus 5 centimeter square per second. Okay, so in this one can see like some water model like the BF water model, BNS water model, okay, and SPC water model. So these basically overestimates the diffusibility. Okay, and after that, like few water model, okay, so SPCE, so T5P, and SPCAF. So these water models are reasonably well in terms of diffusibility of water. Okay, so after that, the main thing which comes like one of the main thing, okay, so which is the microscopic structures of water. Okay, so these thing, this microscopic structure, or one can say this RDF, like first, as you know, like the structural data, like experimentally comes from the X-ray and the neutron scattering experiment. Okay, so for that thing, I want to say something like people, if we coming back in early 80s, like 1980 or 1990 at that time. Okay, so as an experimentalist, come with different they plot the RDF and they come with a different value. Like some group like Narton and Levy, so they perform an X-ray experiment and they give a value. They plot these G oxygen correlation, and which comes around the first fix comes around 2.2 angstrom. Okay, so and then few later on, and another group do the neutron scattering or neutron diffraction experiment. So they got the value of 3.1 angstrom. So even these experimental things, so these are not settled at that time. So like to make a water model and validate their value, okay, so with this experiment is not that easy at that time. So because the experiment is also uncertain at that time, like later people do uh, experiment and they settle down in a value, and at that regards and that value regards, uh, in this review paper they have plotted, they have scored, uh, assign a score for every water model. Okay, so if it agrees bad with this experiment result, then gives -1, and if reasonably good, then 1, if better than that, then 2, and if best, then gives 3. So if you see this DEC model gives better agreement with this experimental value, so almost equal to experimental value. Like if you see like SPC, TIP3P, so these are just acceptable at that time. Okay, and SPCE, T4P, so these are, we can say, like with good agreement. Okay, and if I see like T5P and DEC, so these models is really accurate. Okay, so with this experimental value. Okay, in terms of this water structure. Okay. After that, if I see the main thing, which is the density maximum. Okay. So as you all know, like the water density maximum near 4 degree centigrade. So which is a very anomalous properties of water. And at that time, no water model can able to produce this exact value. Okay, so not for water, not for D2, and nothing. So if you see this value, so the solid line, the solid dot is for polarizable water model, and the circle is for rigid water model. If you see, and these three things, this is for water. So if you see, no water model can able to produce that thing. Okay, so if based thing can come, so it's around 14 degrees centigrade. Okay, so like 14 degrees centigrade, you can able to like T4 PFQ, they can able to produce this maximum density. Okay, so and this is something. After that, like if we see the critical parameter, so like as you know that due to the presence of hydrogen bonds, so water shows some high critical temperature value. Okay, so around for water this critical temperature around 647.1 Kelvin. So if you see for this experimental value, so no, these water models are distributed. Okay, so not only of one region. So these results are very scattered for this water model. So no water model can able to produce uh, this exact critical temperature value of water. So these are the few tests people do for testing their water model. And not only that, if people try to calculate the dielectric constant, so if you're also able to see that dielectric constant values for these various water models is also very scattered. Okay, so after showing all these plots, so one can able to conclude something from that. So it's the feeling for this active 40 years of research. The feeling is we can make few conclusion from that. That the first one is like semi-quantitative reproduction of this water property. So that can one can uh, calculate or one can get from the computer simulation experiment by formulating by producing simple empirical intermolecular potential for water. But in that regard, you have to compromise between the simplicity and accuracy uh, for for this uh, like validating points. Like some water models is good to produce the structures, some water model is good to produce the diffusibility, some water model is good to produce this critical point. Okay. Okay, so this maximum water density and the critical temperature is no water model can able to produce uh, good. Okay, so in that context, like after this 30 years of active research, so scientific community uh, comes with few conclusions, and they comes with these few questions. Okay, so it's time to address few questions. So few of the questions are solved in the recent years, like not recent years, so it's after that time. Okay, so at that time, like as you know, there is a large amount of ab initio calculation like devoted to design the force field between the water molecules. Okay, so as I discussed earlier, so like the CPMD calculation by Parinano group at that time comes, and which becomes quite impressive at that time. Okay, so but at any point of time, this type of calculation is always very time consuming, and you can compare. Okay, so with respect to the what empirical water models, so for the system which is more realistic system size and for which the larger time scales are needed. Okay. Okay, so but nevertheless, these ab initio calculations are quite relevant. Okay, so when you have to tackle like some quantum interactions and that things, but apart from this, like if you address few questions, okay, so then the first things, like when people at that time, when people making the water model, so they assume a hypothesis, so they consider the negligible covalency of hydrogen bond. So is that hypothesis, like the hypothesis of negligible covalency in hydrogen bond. So is that hypothesis correct or not? So this question comes into mind to people because X-ray experiment in 1999 comes. So in that paper, they have conclude that hydrogen bond in ice is partly covalent. Okay, so this is a very like the theoretical community at that this made a huge impact in the theoretical community because they conclude in their paper the hydrogen bonding in ice is partly covalent. Okay, so that completely discards the assumption of this previously made all the water model, the discards all the assumption that's a purely electrostatic bonding model for this condensed phase water. Okay, so but hopefully later so this they made actually they made a Compton profile of icosidral ice. So like after that this some ab initio calculation prove that this the conclusion of the hydrogen bond in hydrogen bonding in ice is partly covalent, so this conclusion is wrong. So in that context people are working with this, considering this negligible covalency in hydrogen bonding. Okay, so the next things comes into the mind is the obvious thing, like this point charge approximation. So these are the accurate enough to reproduce this electronic charge distribution. So the one word answer is no. Okay, so because you know that the electrical potential, okay, so that's emanating from a water molecule is much better, one can approximate by the diffusive spherical charge density. Okay, so in addition to point charge on the nuclei. So when the equilibrium separation is long, so then it's okay. But when the equilibrium separation between two water molecules is short, so then the interaction energy of two molecule, okay, so with you can say like with overlapping charge distribution, so you can't be well reproduced by these point multiples. Yeah. Okay, so this assumption, like this simple point charge approximation assumption, so might be that's can be a reason at that time people think, so it might be a can be a reason because all the water molecule or all the water model is not gives the exact result, like some are good at that point of time is okay but not that efficient. Okay, and again like people address few questions at that time, like this choice of this Lennard-Jones repulsion dispersion term, is that relevant or not? Okay, so is the charge transfer significant in hydrogen bonding or not? So this question comes into the mind in people, and in later few years like in 21st century people address this question. But one question like which is the one most important question comes at that time, at that point of time, like the introduction of the polarizability, is that too much important or not? Okay, so because if you see this plot carefully, okay, so I read it just a glance, so if you see this plot carefully, so then you can able to see that the polarizable water model, like these are not that good as expected. Okay, so so that time like the main uh, things comes like this introduction of the polarizability into the water model, is that important or not? Okay, so that time some empirical models, as I already told, like SPC, P, or R pole, so that type of water model comes. Okay, so in that water model, the problem is they assumed that the molecular polarizability is unaffected. Okay, so this molecular polarizability is unaffected by the liquid phase, and they can identify this gas phase value. Okay, so in their water model. Okay, so but mainly at that time we will assume, so that can be a problem. Okay, so after that, some quantum chemical calculations uh, to evaluate the perturbation, okay, so generated by the condensed phase. So people come into the conclusion that the mean polarizability in the liquid as compared with the gas phase value, which is 10 to 15% lesser than this gas phase value. Okay, and this decrease of the polarizability is observed. Okay, so and this is mainly takes place in the plane of the molecule. Okay, so which is the along the hydrogen bonds. Okay, so these can be caused by like cumulative contributions of exchange, charge transfer, polarization interactions, and that thing. Okay, so at that time, we will have like scientific community has no answer like why polarizability, introduction to polarizability or polarization effect in computer simulation, uh, not giving any satisfactory result. So after that, we all know like they give some satisfactory result. Okay, and then one can say like in that context. Okay, so in summary, if we say like in that present knowledge, like what I tell, like this point dipole approximation. Okay, so and the gas phase value of the dipole polarizability when dealing with the polarizable model, especially when dealing with the polarizable model. So these can be a reason for this erroneous value. And so these two, if I write, so these two things, one is this point dipole approximation, and this can be a problem. And the another thing is use of gas phase value of dipolar polarizability. Use of dipolar polarizability. Okay, so this thing can make problem in the water model, so which can be addressed like after few years, which people can address. Okay, so like in these 30 years of computer simulation of water, so the scientific community has a mixed feeling. Okay, so there is a like impressive amount of work published at that time. Okay, and okay, so and this we can say like the information, okay, for the modeling of water and that thing, so the information they gathered at that time is quite impressive. But uh, on the other hand, one can say there is a taste of incompletion. Okay, so because one considered that not our water model, okay, so not our water model obviously at that time in the literature is able to reproduce the great accuracy for all the water properties. Okay, so that is a, so that's why I can say, so that's a mixed feeling at the in the scientific community. Okay, so on the one hand, it's a lot of work in the water model, and on the other hand, no, not a single water model can able to produce all the water properties in a single water. Okay, uh, obviously some significant like progress we can able to see in that year. So at that point of time, few water model we can say like these are like kind of okayish at that point of like mm, time. So that's a DEC water model which gives like somehow better. One is Paul 5 water model, and as you all used, that's a SPC water model. Okay, so these water models gives like reasonably good uh, like water properties in every context of water. Okay, so these are the 30 years research, like in very brief. So there is a few papers like and one review paper. So these papers I will send in the group. Okay, so I try to keep things simple, but as you know, like these history things, so everything is connected and it's very difficult to explain. Okay, so at first I think like it's very easy to tell like what happens, okay, after that, but after that I realized that this history thing is very difficult, okay, to tell like what happens exactly at that point of life, what people think at that point of time. Okay, so it's very difficult. Okay, so that's it from my side. If anyone wants to make any comment. Okay, so I made a proper note and even or slides or note, and then I will send it in the group. Okay, so with this paper link, okay, and DOI and link. Okay, so there is various papers in that context. Okay, so if anyone has any question, so you can ask. And anyone has add any information and any feelings, any comments. Okay, so it's feel free to add.
Yes, and to comment one thing, these whole descriptions are perfect. That to describe first that the starting from this Stillinger time
Mm.
and the recent ab initio time,
Mm.
CPMD or CP2K like thing, and now for recently there are a lot of development in the nuclear quantum effect. Means there are
Yes. Mm.
significant for H2O mainly. So this is one development, and means which is not aligned with the earlier gradient, okay, in the development era. But others part is aligned, means in the same line, like those accuracy, increasing the accuracy, like Dominic Marks just published in PRL that CCMD means in
Yes.
cluster accuracy. Yes, means in that line is it is along the same line to improve the accuracy of the model. Means this is mainly because this could be possible due to this machine learning framework. Otherwise, it won't be possible. Means it is imagined to implement with that accuracy. Means it would be difficult. Means they still train for the liquid water, but it is means uh, it is really difficult to imagine. Means even now also means a single model would train all the means water phases, means from the solid to vapor. Means this is even now it is a challenging problem. Means
Yes, so that's why I say like it's a 30 year of challenge, but now I can safely say it's a 50 years of challenge.
yeah, yeah. Now locally we have accuracy. We can get that accuracy for
Yes.
some local means local thermodynamic zone, but uh, in the global, if we want to design some global force field, then it is not till now. Means there is no straightforward framework, no framework, not straightforward. So this is my comment.
So anyone else want to say something?
Yeah, Subhajit, so what is the future of this? Like how we are seeing the future? What
Okay,
should
so
be our next step?
I think it's going on. Okay, so in future also,
But but
because
but all these water models which have been
hmm,
designed to use in classical force field are
hmm.
still relevant now, or is it getting somewhat backwarded?
So I believe like there are like more than 50 water models, but I believe like hardly two or three water model can able to survive more than 2 decades. Okay, so like as you see, like SPCE water model, and so these water models are really good for practical aspects, like for practical problems. So that's why this water model can now also survive. Okay, so again,
Okay, so
I am not sure about the polarizable water model, because if you see this polarizable water model journey comes from long, like from 40 years, if I count from now, so it's 40 years, but still not that impactful. Okay, so I am doubtful about that. That's polarizable. Like the amount of work, the amount of computational power, the amount of work people uh, spent on that polarizable water model to introduce this electronic polarizability, but
mhm,
still not that remarkable improvement. So I am very doubtful about that. Okay, so what is the future of that?
yeah. And I think in the next 5 years, like we will not use any SPC or T4P model anymore.
Mm,
This
That
is
will be in
maybe.
my
also my
opinion.
feelings also same, means that
Yeah.
means due to this machine learning development,
Yes. Yes.
we means those give the mean same similar computational power like polarizable force field, but
Yeah.
lot more accuracy.
Accuracy,
So
exactly. Mm,
so no means if we still use this SPC or means after 1 decades probably, then what
Mhm.
we would accept means why you uh, means when a more accurate and more efficient model is available, why are you still
Yes. 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 And second, so have you heard about the MB pole potential?
MB pool, this Pacini group uses and there,
Yeah.
yes.
Yeah. Yeah.
Uh,
Yeah. So recently they published many papers on that updated MB pole potential.
yes, yes, yes.
So yeah, that is really good, I think, in terms of accuracy.
Yeah, one more thing I want to add that those development, how the development water model, this would be a means good experience to create the descriptor for the machine learning. Means for
Yeah. Yeah.
machine learning depends on the how good our descriptor are. Means it
Mhm.
largely depend on that part. So means this kind of this MB fold or previously discussed the ReXFF, those are
Mhm.
basically those are also fitting. Okay, but some we have to send some means functional from beforehand. So those can guide for more better training purpose in machine learning. So those are important for those perspective means in the development of machine learning potential. So
Yeah.
otherwise means there are no means there means as a sole simulation means simulation with only this potential, these would not exist. Means we can transfer the idea from this potential form and the to the machine learning, but
Mhm.
in terms of simulation they don't exist probably.
Okay,
Uh,
so
so,
yes, Himanshu.
Subhajit,
So mainly those models that you have discussed.
Mm.
I think if I'm not wrong, so all the models that people develop, so they mainly contain mainly what else? It contains only these bonding parameters and non bonding parameters, right?
Mm.
Is there any another term apart from this bonding and non-bonding term parameters
No,
in
that
any model? In any model.
uh, no, I think so. They have used this
So
simple
only
bonding
the
and non-bonding. So they have modified only on into that.
uh, so all over these in different models. So they have made changes or improvements in only non-bonding parameters, right?
They have changes, make
They,
changes.
means all the models
Huh?
like SPCE, SPCFQ,
Mm-hmm.
TIP4P and all. So
Mm.
all the water models, so
Mm.
they are different in only non-bonding parameters,
Mainly in the non-bonding parameter.
right?
Uh,
Are they
uh,
different in bonding parameters too?
uh, that exactly I can't say because I didn't go through all the water model. So
Like what any if you means you might have gone one or two models in detail or something.
because some if you see like some the flexible water models, so in that the they have the narrowing of this bond angle like HOH bond angle. So few water model they field central force model. So at that water model, so they have used like the HOH bond angle is nearly around 100 degree. Okay.
In some models.
In some model. So that changes in model to model. Okay. So that's not a fixed value for every model.
Mm.
Okay.
So, so like see, so uh, so every models like as you said, they can't give every experimental results means
Mm,
accurately. So
no, no.
some are good in giving some experimental values, and some are good in very. So which one you find that was most efficient? Mm.
Okay. So I find that SPCE, DEC, so these two models are, you can say, like based at that time. Okay, so at this early, like at 20th century, so these two model are you can consider, okay,
Means up to
for your
20th century.
calculation,
Up
for
to
your
20th
calculation,
century.
at that point of time. Okay.
I think this polarizable models came after means after that.
No, there are some polarizable model as I told, like this R pole and SPC okay, so these are the few polarizable models, but not like Tinker. They have implemented this polarizability, not like that. Okay, so there are polarizable model, but the main problem is at that time this polarizable model. So they are like almost similar to these rigid models. Okay, the value they have give for these various water properties, so they are almost similar for this. Maybe this pole 5 which comes in the year of 2001. Okay, so this pole 5 is, these are ab initio based force field. Okay, so this gives something better value, okay, some better agreement with this experiment. So if you say me to choose one polarizable model uh, and that point of time, so I will definitely choose this pole 5, okay, ab initio based water model, which I find the best one. Okay,
So
at that point of time.
yeah, the last question.
Mm.
So like every model means many of the models currently they are not they might not be in use in
Yes.
present scenario, right?
Hmm, hmm,
So but haven't they? I mean, so like at that time, as you said, this pole 5, right?
hmm.
So means like whoever developed this pole 5 model, so they might be doing improvement in that model so that it will be in use like in the present scenario as well as in future. So they might be doing some improvement in those models too. Is it?
Y-
Have you? Yeah.
Okay, so if you remember correctly, this Pole 5 model comes from Barn Group. So I think they uh, improved that model. Obviously, so this is the first thing comes in 2001. So after that, they made few improvement about that. But I don't know exactly. Sorry, like people uh,
Oh,
from
yeah. Just
now
like
from now people use it or not. Okay, so
uh,
I came across this like few papers in past, like they've used Pole 5 in 2002 3 that time. Okay,
mhm.
so in recent time, I think no, I think Bongshida can comment like about this Pole 5.
Polarizable recent
Yeah,
time. I have seen polarizable model as Paul VI2S.
okay,
That
Paul VI2S is something I think different. Like this Paul VI2S is developed by this Japan group, and Shinji Saito sir is also involved into that. Okay, so I can't
but for
remember the name.
polarizable model, Amoeba is one you are using, and
Uh,
is yeah, for many body potential, this both developed.
like the poly 2vs is widely used nowadays. Okay, so I can say like more than amoeba for polarizable water model, people use poly 2vs, and poly 2vs is also ab initio based model. Okay, and some Japan professor made this. Okay, so from Japan, sorry, forget the name. Okay.
They means they have parameterized with respect to some spectroscopic to match.
Yes. In that, their first paper, they reproduce this water like IR, Raman, so all those things like, and Himanshu also these terahertz portions also, the whole spectrum like 0 to 4,000 centimeter inverse, they reproduce that one.
so
Okay.
like in amoeba, like they're means constantly doing development in this amoeba model. So currently they have this amoeba and amoeba plus plus and this hippo model.
Yes.
Okay, so and
Hmm.
also they have so recently they have uh, 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 published a paper where they have used this nuclear quantum effects to in their model. So
Yes.
in the same way the other groups means like this poly to VS and other models. So also why they are not means I'm not sure whether they are doing it or not, but means they might be doing this same improvement in their model.
But
Yeah, I'll
maybe
see.
like I
I'll see.
didn't come across any
Yeah.
improved poly 2vs model.
Mm.
Okay, so I don't know. I think
Okay.
if I'm not wrong, then this poly 2vs comes around 2007 and 8 that time.
Mm.
Okay, so if I'm
Mm.
not wrong. Okay, so after that, mm, I didn't find any paper or anything. Okay, so about this poly
Yeah.
2vs, but people use poly 2vs efficiently
Mm.
for these, at least for these spectroscopic calculations. Okay, so people use poly
Yeah, means
2vs.
those are the best model, means poly 2
Best available polarizable
a
model,
very,
you
a
can
very
say.
polarizable
Okay.
model. And if you want that best non-polarizable and rigid model, then this TIP 4P 2005, this Carlos Vega paper, he actually rank means as Subhajit shown that means no models can give the all properties accurate. So they rank, they score the model based on how many property they predict accurately and not. So in that rank, TIP 4P 2005 got the highest rank. So they told that, but again, this, if we are focused on this, if we are focusing on this dynamical property or spectroscopic property, we take SPC, means there is no. So now it is means those polarizable and rigid model are used, but my feelings is that amoeba also it will take also take its turn towards this machine learning. Means just like in similar concept, they use those electrostatic multipole, but in the fitting part, they will do with machine learning. Means this is my feelings. So nobody would stay in that simple functional form or normal ab initio is difficult. I mean, very accurate. Means in the ab DFT, we can see that even in DFT, one pseudo potential to another pseudo potential, huge change in the property. So this is not accurate. Means you cannot. So for a particular property, one functional is more accurate than others, and for other property, the trend change. So every means machine learning will means overpower everything.
Okay, sir.
Okay, so any other want to share something? Okay, so then we can discuss about the next